Okay, this question comes from January 2006, Module 4, from the old specification. It's question 2 on specific heat capacity, and it starts off with just a definition of specific heat capacity. So, specific heat capacity is defined as the energy required. In fact, you could probably put the heat energy required to raise the temperature. To raise the temperature of 1 kilogram of a material by 1 degree Celsius or 1 Kelvin. So it's the heat energy required to raise the temperature of 1 kilogram of a material by 1 degree Celsius. We then come to a calculation. Electric drill used to make a hole in a piece of copper. During this operation, the drill uses a current of 2.5 when it's connected to a 230 volt supply. Mass of the copper is 0.65. 55% of the electrical energy is converted to heat in the piece of copper. Right, so what we're going to say here is that the 55%, so that's 55 over 100 of the electrical energy is equal to the heat energy that goes into it. And we can then use our specific heat capacity equation. Well, the electrical energy we know is, so it's that's 0.55, 55 over 100, 0.55. The electrical energy then is going to be equal to, well, E, the electrical energy equals ITV, so that's 2.5 times the time, which was 15 seconds, times V. The voltage is 230. Okay, so that's ITV, that's where that's coming from. And that's equal to M, the mass, so it's M times C times delta T. So it's M, the mass, which is 0.65, times the specific heat capacity, which is 380, times delta T. Therefore, delta T is equal to 0.55 times 2.5 times 15 times 230 divided by, and then that's 0.65 times 380. Fill all those values in and we get that delta T is equal to 19.2. So a temperature rise of 19.2 Kelvin. We're then told to assume that the figure of 55% for the conversion of electric energy is correct. State whether the temperature rise in your answer is greater or less than what occurs in practice. Well, the temperature rise is likely to be greater because there'll be some heat loss to the surroundings. So there'll be heat loss to the surroundings from the drill bit. And so, well, if we've lost some heat to the surroundings, then we're saying the specific heat capacity of copper is 380 joules per kilogram, and we're dividing by that. So if the heat loss to the surroundings is likely to be less than that, then that means that the temperature rise, the electrical energy that we have used to calculate that will be bigger. Therefore, this figure that we're using is like, so because there's heat loss to the surroundings of the railway, and so the temperature rise in B and B above will be greater than in reality. And if we just look at our calculation for that, what we're saying here is that 0.55 should be a lower figure, so here that's making it bigger, and therefore we're going to have a slightly greater value than we should have in practice.